this video, we're going to be talking about relations. See what I did there with the cute little couple hugging because they're in a relation? Isn't that cute? Okay, a little punchy. It's the weekend. So we're going to talk about relations. A lot of the terms we're going to talk about will sound a little bit like functions, but these are not functions. They're weaker than functions. But we are working on developing definitions for functions, so you're going to start to hear some familiar terms. But first off, let's define what a relation is. Van Beer sets a relation R from A to B is a subset of A cross B. So to put it more clearly, R is a subset of A cross B. For example, let's say I have A is equal to the set alpha beta and B is equal to the set XYZ. One possible relation I might have is alpha X and beta Y. Another way of saying this is if we know the relation is called R, we might say alpha Rx, or alpha is related to X, and beta Ry, or beta is related to Y. For me, it's a lot easier just to say alpha X is an element of R, because all the related to gets kind of funky. That's only one relation. How many relations can we come up with? So I know my A has 2 elements, my B has 3 elements, so A cross B is going to have 6 elements. R is a subset of A cross B, which means the number of possible subsets, which is the size of the power set, is 2 to the 6, or 64 possible relations. If R is a relation from A to itself, then we just say R is a relation on A. The domain of relation is a set of X in A such that there's a Y in B, such that XY is in R. So in other words, it's whatever appears in the first slot. And the range is whatever appears in the second slot. So let me give you an example. Let's say we have the relation 2 alpha, 2 beta, and 3 cat, because I had some weird sets. The domain of this is equal to whatever shows up in the first slot. So the domain is just 2 and 3. The range is whatever appears in the second one. So I have an alpha, I have a beta, and I have a cat. So that's the range. So it's pretty straightforward. There are a couple of special relations we want to talk about. There is the identity relation. It's just the set of A comma A, where A is in little a is in big A. So if my set A was equal to the set alpha beta, I think that's what I had, then the identity on A alpha beta beta, you just double it up. If I have B and that's equal to 1 2 7, then the identity on B is 1 1 2 2 7 7. Another relation we care about is the inverse relation. Now, when we do functions, we care about if it's a function going one way and it's 1-to-1, then it's a function going the other way, and that's going to be 1-to-1. When we're talking about relations, we don't care about any of that. The inverse of a relation is just where you switch the ordered pairs. Instead of being XY, it's now going to be YX. So the inverse of the identities are boring because it's still going to be 1 1 BB 2 2 7 7. But let's say I have this one, and I want R inverse of this relation. I would have alpha 2, I would have beta 2, and I would have cat 3. Notice the domain of R will equal the range of R inverse and vice versa. The domain, can't spell it, of R inverse will equal the range of R. The next thing I want to look at is composition of relations. Now this definition is not very clear when you just read it. I'm going to show you an example or 5 before we actually do the definition. Let's suppose I have the relation R and it is 1 5 2 2 3 4 and 5 2. I don't know what the original sets are. I'm going to let S be another relation. It's going to be 2, 4 and 3, 4, 3, 1, and 5, 5. So let's say I want to do R composed with S. Just like with functions, when you learned this way back when and messed it up then, this means S goes first. Then R. We go backwards. S is acting on something and then R acts on it. That's why that happens. So let's have a visual of this. That's not big enough. Yes, it is. The domain of S is 2, 3, and 5. And it goes first. Let's make its range a little bit bigger. It goes to 1, 4, 5. Really didn't need to make it that much bigger, Megan. Now, the domain of R is 1, 2, 3, and 5. 1, okay, I don't have a 2 or 3, but I have the 5. And its range is going to a 2, 4, and a 5. So this is my R. Let me write down the relations here. I have 2 goes to 4. I have 3 goes to 4. 3 also goes to 1, and 5 goes to 5. I filled in all the connections for S. Now the connections for R, I've got 1 goes to 5. I have 2 goes to 2. I have 3 goes to 4. And I have 5 goes to 2. To find the composition, you're trying to find ways of starting over here and ending over here. Anytime you've got a path, you'll have an ordered pair. So let me by that. I'm going to start here with 2. 2 goes to 4, but 4 goes nowhere. So we're screwed. That's a dead end. So let's look at 3. 3 goes to 1, and then 1 goes to 5. Yay, so we have the ordered pair 3, 5. 3 also goes to 4, but we already know that's a dead end, so that's it for 3. Let's try a different color because this is fun. I have 5 goes to 5, and it will show up. And then this 5 goes to 2. So I now have the ordered pair 5, 2. Nobody goes to 3, so that's, would you call that a cul-de-sac? That's not going to get us anything. And we already said nothing goes to 2. 4 is a dead end. So that is my composition. Let's try going the other way. And I'm going to write a different picture because, okay, so let me run myself. I have R. This time I'm going to start with R. And R has a domain of 1, 2, 3, and 5. And R is going to 5 because I'm OCD, a 2, and a 4. Now let's deal with S. S needs a 2, which we have, needs a 3, I'll just stick it here, and a 5, which we have here. And it goes to, and it goes to a 1, and a 4, and a 5. Let's do our relations. 1 goes to 5, 2 goes to 2, 3 goes to 4, and 5 goes to 2. Actually, there's a function. Okay, and over here for S, I have 2 goes to 4, 3 goes to 4, 3 goes to 1, and 5 goes to 5. I can already see that 3 is a dead end because nobody's going there. 4 is a dead end because nothing leaves that station. I really need to do that. I want to keep my eye on it. Okay, so let's try this neon orange. If I start with 1, 1 goes to 5, 5 goes to 5. So I have an order here, 1, 5. 1 goes nowhere else, 5 goes nowhere else. Okay. 2, 2 goes to 2, which goes to 4. I didn't change pins, oh well. And that's all that 2 does. 3 goes to 4, nowhere else. 5 goes to 2, 5 goes to 2, and 2 goes to 4. So I have 5, 2. So this was S composed with R because R went first. And that's how composition works. Now, some people do this thing in their head. I'm not as good at this. If you want to say R goes first, some people go 1 to 5, and then 5 goes to 5. There's 1 to 5. No other 5s here. 2 go to 2, 2 goes to 4, 2 goes to 4. They can do it by looking at the order of pairs. For me, I like to do it this way so I can see them all, in case they get sort of weird and cattywampus. So notice that means if you have R composed with R inverse, or R inverse composed with R, these are going to go A goes to B, then B goes back to A, so you're just back to A again. So this is the identity. I didn't talk about what their sets were, but it's the identity of whatever set we were talking about, whichever we're going from. Without further ado, let's look at this definition from hell. The composition. If R is a subset of A cross B, and S is a subset of B cross C, then the composition of R and S is, well, S composed with R is the ordered pair AC, where there's a B in the middle, where A goes to B and then B goes to C. So it kind of makes sense if you read it that way. It's like B is the stepping stone. If they have a stepping stone in the middle, you start A way over here on the left, and then the C's are over here on the right. Oops, on the right. And if there's something in the middle B that I can actually bounce on, then it's going to be in the composition. So with that said, let's look at some theorems. Let's look at some theorems about relations and compositions and all that kind of good stuff. Suppose A, B, C, and D are sets, and R is a relation from A to B, S is a relation from B to C, and T is a relation from C to D. Then, first off, R inverse is R. The composition is associative. I will show you this in class, the proof for this. Conceptually, it's not hard. Technically, notationally, it's a pain in the ass. If you do the identity composed with R, you get R back. If you do R composed with the identity, you get R back. This I sub A and I sub B is just making sure you have the right identity on the right set. But basically, if you have the identity composed with another relation, you're going to get that other relation back. It's one other reason it's called the identity function. And if you do the inverse of a composition, the order switches. It's that whole shoes and socks thing. If I put on my socks, shoes first, but if I put on my socks and then my shoes, if I want to do the inverse of that process, I have to take off my shoes first, then my socks. So the order switches when you do inverses. So that's a little bit about relations. We can talk about some more relations for Wednesday's class, and I think this is a good place to stop. Thanks.